Hello, we're Piotr Kozłowski
And Veronica Vanek.
from Group AP, and today we're presenting our FPGA-based Pong game. Before we dive into the technical details, let's first see what we've built in action.
So here you have our multiplayer Mandelbrot Pong game. On the top you see you have player 1, and on the bottom you're going to have player 2. They have different colors to differentiate between them. So in order to start the game, it's player 1 that starts. And so you can see that the game has started. The game will reset once somebody loses. So I'm going to try to show the controls of the top paddle. So once the game has started, as you can see here, we're pressing other buttons, but the game is not starting. So you need to press both buttons in order to get it to start. The right button is going to move to the right. It's going to move the paddle to the right. The left button is going to move the paddle to the left, and the same for the bottom ones. So the third button is going to move the paddle to the right, and it's a bit difficult. Start the game, and then the paddle is going to move to the left with the leftmost button. And aside from that, we're now going to attempt to be playing as two people.
We can play.
We can play. Okay,
Ready?
this is not very easy with only 3 hands, but Piotr is very good, is a very good gamer. So now we're playing.
Pro gamer.
I better pay attention to the game. Oh no, he's lost. And that's it. That's our game. And once again, one more attempt at a loss just to see what it looks like. That's it. It resets.
We stuck closely to the proposed architecture, implementing each module week by week in structure progression. This methodical approach ensured that each component was tested before integration with the next module.
So now we're going to look at the VGA controller logic. On the right, you see how the horizontal timing works, and the vertical one is very similar. So the display region is where we actually draw the pixels, and after that we have the front porch, the horizontal sync pulse, and then we have the back porch before the next line starts. The code shows how it is implemented. So the horizontal counter will increment at every clock cycle, and when it reaches the end of a complete line, so the display plus the front porch plus the sync pulse plus back porch minus 1, it will go back to 0. And otherwise it will just keep counting up, and that's how we're able to scan across each row of pixels. As for the RGB output, we are going to check if we're in the visible display region. So if VCount and HCount are both within the display boundaries, and if that will be the case, then we will pass through whatever color value are coming in from the game logic. And if we're outside the regions, so in the porches or the sync areas, we need to output black. The monitor doesn't show them, but it's necessary because we're not wanting to send garbage data. And the same pattern will repeat vertically, and so we will have the complete frame timing that the monitor needs.
In Lab 6, we implemented background frame buffer. We use a dual port RAM as a frame buffer between the Mandelbrot generator and the VGA controller. On port A, the Mandelbrot module writes pixel data into memory. The write enable comes directly from the Mandelbrot core, and the memory address is found by concatenating the Y and X coordinates after dropping the two least significant bits. This effectively divides both X and Y by 4, implementing pixel scaling. On port B, the VGA controller continuously reads from memory. It uses the same scaled address mapping, so each memory address corresponds to a 4x4 block of screen pixels. The memory output stores packed RGB values, which are then split into red, green, and blue components for display.
Now we move on to the game logic. Our FSM has 3 states: idle, playing, and game over. First, I will do a high-level overview of how it works and then go into the details. So we start in the idle state right after the reset is hit, and to start the game you press both the main player's left and right buttons. The reason I specify left main player is because initially our FSM only had 2 buttons for one player, so when we added the 2-player logic, we kept the same buttons. So once the main player's buttons are pressed, we transition into the playing state. In the playing state, at the condition of the ball touching the top or the bottom and not being on the paddle, the game will end and the state will switch to the game over screen. This will stay there until both the main player's left and right buttons are pressed, which brings the state back to playing once again. We chose this architecture because it's similar to many arcade games. There you can immediately start playing once more, and you don't have to pass by an intermediate step. And initially we were going to add a score as well, and this was easier in this type of architecture. So let's look a little bit more in detail on what actually happens. When the reset is hit, the ball becomes centered, stationary, the paddles are centered, and the game waits for player 1 to start. When player 1 presses both of the buttons, left and right, and it wasn't held before, then the game transitions into playing. At every edge, which is calculated once per frame, the P1 and P2 paddles move synchronously, and the ball direction will be calculated according to the ball their X and Y. There is collision logic that the ball can bounce after colliding with the sidewalls, and it can also bounce off of the paddles. If it does not do any of these things, it will fall through the screen and the game will be over. The movement logic is left equals 1, R equals 0, it moves right, and L equals 0, R equals 1, it will move to the left. So once the ball passes the top edge or the ball passes the bottom edge, the game will end, and we will be waiting for the buttons to be pressed in order to restart again.
Now the sprite logic. This module draws 3 game objects, the ball and 2 puddles. For each pixel, we check if it falls within a sprite's bounding box using simple coordinate comparisons. If the pixel's x and y coordinates are within the ball's bounds, we draw it. The same logic applies to both puddles using their respective position and size parameters. When a pixel matches in a sprite, we output a draw signal. Otherwise, the background shows through. In Lab 8, we've built a hardware Mandelbrot generator using the FPGA state machine. It processes each pixel to determine how many iterations it takes to escape, creating colored fractals you see here. To test the correctness of our implementation, we tried to generate Mandelbrot image with provided test bench, and here you can see this image. Firstly, in init pixel state, we start by initializing a new pixel. All counters reset to 0. The real and imaginary parts of our complex number start fresh, and the iteration counter goes to 0. In iterate state, we calculate the Mandelbrot formula repeatedly. Each iteration, we check if the magnitude squared exceeds 4. If it does, the point has escaped and we're done. If we hit our maximum iteration limit, which is also 4, we're also done. Otherwise, we update Z and increment our counter, repeating until one of these conditions is met. Finally, in write pixel state, once iteration stops, we output the result. The iteration count becomes the pixel's color value. Then we increment our position counters to move to the next pixel and loop back to init pixel to start over. This 3-state cycle generates the complete fractal image, with each pixel's color determined by how quickly it escapes the Mandelbrot formula. For our extra feature, we added a second player to the game. The second paddle appears at the top of the screen in a different color, giving us true competitive gameplay. Each player has independent controls. The first player uses their original buttons, while the second player gets 2 additional buttons. The result is a fully functional 2-player game where opponents can compete in real time on the same screen.